Hi everybody, welcome back. It's been a minute, but I've been very busy at work and it's only getting busier. I'm short one employee, so I've been out in the field a lot myself carrying a toolbox. Not that I don't always do that, but even more so than normal. And just haven't had a lot of time. But believe it or not, in the background here, I have been working on this an hour here, an hour there in the evenings, just when I want to unwind and work at the bench. And we do have the power supply completed. I'm going to show you this in a minute, and we're going to have fun with power supplies today. This is going to be a really interesting video for those of you who are interested in building or servicing vacuum tube amplifiers. There will be a lot of good information here. But before we start playing with high voltages, I have to make two disclaimers. First one is safety. And that is, we're going to be working with absolutely lethal voltages today. Upwards of 560 volts with a transformer and power supply that can deliver up to an amp or more at that 560 volts. If it gets across your heart, it will kill you graveyard dead in short order. So it's no joke, and it's nothing to play with if you're not familiar with working with this kind of thing. Now, some of you who watch my channel are probably better at this than I am, so this is not a big shocker to you, no pun intended. But for those of you who are just getting into the hobby, I would suggest working with smaller tube amplifiers, little single-ended ones with a single 6V6 or something like that. Those still have high voltages, but nowhere near what this one's going to do. So I just had to put that out there. Be careful. There are safety tips out there. There are those of you who will see everything I do and want to critique my safety practices. All I can say is I'm doing what I'm comfortable with, the way I've learned to do it over the years, and I'm very comfortable in what I'm doing. Just understand, no matter what kind of safety practices you do, you always run a risk of making a mistake and ending up getting hurt. Never put yourself in that position where that getting hurt will cost you your life. Look it up. There are plenty of videos and things out there and a lot of information out there on safe practices around high voltages. So that's enough of that for now. Not trying to scare you all, but in some ways I am. All right, next, the circuitry that you're about to see is not the only way that you can do this. As a matter of fact, there are much more common ways that you can build this power supply. Remember, when I started this Hedge amp project, this is something to satisfy a curiosity that I have had for almost 30 years now, ever since I read that Morgan Jones book entitled Valve Amplifiers. I saw that blurb about the Hedge amplifier. I read some information about some of the techniques that he experimented with for power supplies. And this is a giant experiment platform. My goal of this is not to build the greatest stereo vacuum tube amplifier ever built in history. It's to learn about the concept of how this works and to, again, satisfy my curiosity on the Hedge amp and on some of the practices for power supplies. So again, there are other simpler ways to build these power supplies. I'm going to show you some things that will be some good techniques that you can kind of integrate into some of your future projects. So it might be interesting to you. Anyway, I'm going to go in great detail on how each of these circuits work. And if you're not into great detail and things like that, this might be one you may want to use the skip button a little bit. I will not blame you for that because, again, this has to be something you're really interested in for you to be able to sit through it without falling asleep. Fascinates me, and I know some of you out there get fascinated by it as well. So, without any further ado, let's look at what we have. Okay, here we are at the 30,000 foot eagle eye view of the power supply. And yes, there is no circuitry on here yet that is part of the actual amplifier circuit. As you can see, all the sockets are empty for the most part, except for the filaments and power related things. So this entire circuit that you're looking at here is just power supply. Now you're going to see why in a little bit, because we're going to refer back to the amplifier a little bit and try to understand why this has to be this way. I did have to make a couple of changes. One of them was one I had to make. The other one was a choice that I wanted to make after kind of experimenting with this a little bit. So this is one thing I forgot to mention, so I'm going to mention it right now. If you look right here, I had to remove that isolation diode that I talked about in the previous video and just replaced it with the jumper. You can see it right there. And then if you see the two black wires up there, there's another pair of diodes. Those are going to the actual chokes for the choke input power supply for the 300 volts. I had to do this because that original circuit did not work. Even though I had that isolation diode in there, the capacitors on the other side of it were holding the voltage high at that point, so I was not getting that AC ripple that I need to make the chokes work as a reactor. So I hope that makes sense. You'll see it in the schematic, the modification I made, and that's what it is. You can see these are just this little section right here. This is the 300 volt regulated supply for this channel and for this channel. And then this one back here is basically all the other power supplies on that board. As you can see, the potentiometers are mounted for the bias supply, and the feeder for those would be these orange wires that are not connected. They'll go into the bias supply when we build that. But the voltage, the negative 150 volts source, is right here for those. This extra transformer is for the elevated filament supplies, the elevated 6.3 volts. So the two output tubes, the KT88s, those are going to have a regular 6.3 volt power supply, and they are going to be referenced through a resistive divider, a couple of 100 ohm resistors you can see there, to ground. So these are ground referenced filament supplies here. In addition, U2, vacuum tube U2, which is the lower part of the cascodes, those are referenced also to ground, 6.3 volts. The other ones, which is U1 and U3, those have elevated supplies, and you can see the brown and the gray wire here. Those are going over to our elevated supplies, and we'll see these later. We'll measure them and everything. They are the center taps of the 6.3 volt windings. There's two sets of 6.3 volt windings on this little transformer, and one of them has been elevated to somewhere around 90 volts. The other one has been elevated somewhere around 110 volts. And that is because the cathodes of these vacuum tubes are going to be elevated way above ground also. So you want your filaments to be similar in reference to the cathodes. If you have a big difference between your cathode and your filament, that cathode filament voltage difference will actually damage the vacuum tube. So that's why you do elevated filaments. And you can look that up. I talked about it in the previous video, so you can go back and watch that. Now you can see these yellow wires are the outputs of the 300 volt supplies, and I have a couple of resistors attached to them temporarily to act as a load, because what we want to do is we want to power this thing up and put it under load in a similar manner to what it would see when it's actually connected to the amplifier. To my surprise, this power transformer is extraordinarily stiff. In other words, it does not sag. I don't care what kind of load you put on it, it does not want to sag. I could probably drive a much larger power amplifier, stereo amplifier, than I'm driving right now. This thing's probably going to be between 50 and 60 watts per channel. I could probably drive a 75 watt per channel amplifier very easily with this same transformer. Here's all of our components on the board, and like I said, I made a change over here, and we'll talk about that later. And once we power this up, we'll measure this. And I even have my 1x100 probe out, and we're going to use it to actually scope some of these, because it's really going to be interesting how the choke input power supply works on this 300 volts. It's not necessary to have that choke. You can actually use a resistive dropper, but the resistor would get very hot. It would have to be a very high wattage resistor, and it would waste a whole lot of energy or a whole lot of power. We'll talk more about that as we look at the design. So what I'm going to do is I'm going to clear the deck here. I'm going to put a big print of the power supply up here on the bench, and we're going to kind of follow through the signal path and kind of look at what this thing's supposed to do when we power it up, and then we'll measure it and see how close we are to what we're predicting. And I'll probably go through a little bit of the math on it. I'll try not to get too much in the weeds with that, but unfortunately, to understand some of this, you will have to do at least some algebra. So you will need to do some math when you're designing a power supply. Yes, this looks crazy, but when you see how many different voltages we need to be able to run this thing, you'll understand why. So let's look at the actual schematic. Okay, so here's where we are, and I do have some notes on here, and I'll back the camera out to see them when it becomes relevant. But let's start at the very beginning here. This is generally what I have. I do not have a soft start circuit, and I'm not going to probably need one because of the way this supply is designed. It's pretty slick. There will be an inrush current in the beginning, but it will not hurt the transformer or any of the components at all. The amplifier itself is designed to withstand the peak voltages that you will see in certain places before the tubes warm up and start conducting. It won't hurt them. So that is one thing that I was able to do. So that's one complication I was able to avoid. So it comes in here, and again, we went over all this before, but I did make a couple of changes that I want to go over with you, and I want to go over some of the theory of how this thing works. You can see how many diodes there are in the beginning here. And if you follow the current paths, you will see that their outputs are all kind of isolated. They share a ground, but they're actually going to different parts of the circuit, and so they really don't interfere with one another that much. Let's start with the simplest one, which is the B+ supply, because it's very similar to any other normal high voltage supply in a vacuum tube amplifier. We have a full wave rectifier. So your center tap goes to ground, and it's 400 volts from either end to the center tap. So it's 400, 0, 400. So your RMS voltage is 400 volts, all right? With as far as when we're talking about a full wave rectifier. Now, to calculate what kind of DC voltage you're going to get, the input is going to look like this. You have your AC sine wave. The output after the diodes, if there was no capacitors or anything, is going to look something like this. You're going to just have this bottom half cycle is going to be flipped up, so every half cycle will be going positive. That's really the purpose of these diodes, is to steer every single half cycle to be positive. So this never crosses the 0 and goes negative. So it is no longer what we would call an alternating current, but it is a changing current. In other words, the voltage goes up and down in amplitude, but it never changes polarity, if that makes sense. It always stays positive. So this ground, this point here is always going to stay positive with respect to this point, if that makes sense. People get hung up on this a lot, and they try to call it AC, and they try to call it all these different things, but that's really what's happening. And that's what this little chart represents. Now, RMS is the way your meter measures voltage. So what do I mean by that? When you're measuring AC voltage with your meter. It doesn't have to be a fluke. Any AC voltmeter. Okay, I can use my old cheap Tenma. It doesn't matter. When you read AC voltage, it is always going to read the RMS value. Now, before you guys flip out on that statement, yes, that is provided that you're using normal mains sinusoidal waveform voltage. Okay, if you start getting into a non-sinusoidal waveform, then you need what's called a true RMS meter that can actually compensate for that. But we're just going to talk about mains voltage right now. We're not going to get into all that other stuff. So your meter will measure the AC voltage in RMS voltage. That is an average. So what it's saying is it's looking at the average of all these peaks. So why would you do that? Well, it just so happens that the AC RMS voltage of a sine wave, or the RMS voltage of any repetitive signal, is going to be equal to its equal DC level. So what does that mean? 400 volts RMS is the same, will do the same amount of work and provide the same amount of power as 400 volts DC. That's why we measure AC voltage in RMS. So 400 volts RMS will give you the same wattage as 400 volts DC, if that makes sense. All things being equal. So now that you get that, well, here's the problem. That is telling you the average of these peaks, but it's not telling you what these peaks are. And why is that important? Because what's going to happen is those peaks are going to go in here into the capacitor bank, and they're going to begin to charge these capacitors. And these capacitors will get a higher and higher charge between ground and between its positive plate, or the positive terminal of the capacitor. These are just two caps in series because I wanted to make them be able to handle higher voltage. A 400 volt cap with 565 volts would not be very good. So anytime you put caps in series like this, and they're the exact same value, the capacitance from here to here will be 1/2. So you now have these two in series would equal 110 microfarad capacitor, but the voltage will double. So now I can have a potential of up to 800 volts between here and here instead of 400 volts. All right, that's the only reason I did that. You could just use one big 800 volt capacitor, 630 volt capacitor if you can buy them, but they're super expensive and hard to find, so it's easier and cheaper to do it this way. Told you I'm going to talk a lot about this stuff. We're going to go into details that some of you already know. So anyway, I'm not going to get into how you derive the square root of 2 and all that for converting, but there is a very simple algebra formula that you can use, or actually just mathematics, just basic math, a multiplication, to calculate the peak voltage. And that is, you take your RMS times 1.414, or the square root of 2, and that's going to give you your peak voltage. So 400 volts times 1.414, or times the square root of 2, whichever you want to refer to it as, is going to be about 565 volts. And yes, for those of you who are perfectionists, 565.6, I think is what it is. But we're just going to call it 565. So we have 565 volts DC here now, because these capacitors are going to charge all the way up here. Even though there's like only a little period of time where you have that peak voltage and then it drops back down, it's still going to see that, and that capacitor is going to charge up to that, and it's going to hold that level until something here hooked up at the load starts to drag it back down or discharge the capacitor. And the idea is you want this capacitor to hold so much charge that it's like a big bucket full of charge, and this thing will empty the bucket more slowly than this will fill the bucket. And then that way it will always stay at its peak voltage. Now that's not how it always usually works, because what will happen, or always usually, yeah, Yogi Berra, eat your heart out. What they do normally is they'll put a little bit undersized transformer, and that transformer will sag. So when you start drawing a lot of current, the transformer can't keep charging the cap as fast as the load is discharging the cap. So that'll drop a little bit. So usually under load, this will drop. It can drop substantially. I mean, it can go clear down towards 400 volts. It can get way down there. So your unloaded voltage and your loaded voltage on a power supply are usually two different voltages. Your unloaded voltage will be the peak, and your loaded voltage will be something between your RMS voltage and your peak voltage. It'll be somewhere in between there. And who knows what it's going to drop to, because you don't know what kind of resistances are in here. You don't know what kind of sag the transformer is going to have when you put too much of a load on it. So all those things factor into that. I will tell you a little spoiler alert. This is a nasty power transformer. It has a huge current reserve, and it's very good at surge current. It's a toroidal transformer. It's very large, very heavy, big windings, overpowered. So what's going to happen is, I predicted this 565 was going to drop somewhere around 520, 530 volts, something like that. I figured it would drop off about 30 volts or so. Fact of the matter is, when I put a big load on this thing, and we're going to do this, it only drops 20 volts. It goes from 565 to about 545, and that's with 110 milliamp load on there. So I had like a 5K giant resistor bank on there, 5,000 ohms, and it still did not pull it down as far as I thought it would. It pulled it down a little bit, didn't pull it down a whole lot. Okay, so the B+, when the KT88 tubes, and let's look at this for a minute. Here's your amplifier. When these start to conduct, and we get our bias set properly, these are going to draw somewhere around 50 milliamps or so. Okay, you're looking at maybe 100 milliamps total, because if you go 50 milliamps on each side, that's going to be 100 milliamps total. I think that's about where we're going to be. It might be a little bit lower, a little bit higher. And you got two channels. So there is a possibility that this will drop a little bit more when I connect both, because I will be actually drawing more than 110 milliamps total if you connect both channels right and left to that. So maybe I'll be closer to my 520. I don't know. I haven't gone that far yet. So we have 565 volts here until it gets loaded down, and it's going to drop somewhere between 530 and 545. And that's pretty much what we need. All right. So really, this part here, you take all that out and you just look at this line right here. This is a standard pi network high voltage supply for a vacuum tube amplifier. You have an input capacitor that's a lower capacitance to limit the inrush. You have a resistor, and that'll be kind of a current limiting resistor. In this case, it's 47 ohms, and I have a 20 watt. It won't even get lukewarm because you're only going to draw maybe a watt or less than a watt. And then another bigger bank. There's actually 4 of these here. So they're 220 microfarad over here. And that's a lot of capacitance. So that's really your basic pi network. All right, that's enough talk about that. That's the simple part. Now, to drive the bias, so you notice we have to bias the input of the amplifier. And we'll talk about all that when we build the amplifier section. But you need a negative supply for that. And I made it 150 volts actually, because we can always adjust this resistor if this is too high. but we never want this to be too low. We need enough bias voltage to make it nice and stable here and to be able to get this down to where it needs to be so it's not idling so high that the tube red plates during idle. And that's what this bias supply is going to do. It's going to set the operating point of this thing where it idles. And that's this circuit up here. And you can see I'm picking off of one of the windings. There is a 70 volt winding tap on each of these. And I could probably mess around with those and try to do something, but this is a very common practice. You can take a diode, put it in backwards, so that's going to make a negative voltage there with respect to ground. And I'm just using a UF4007 or a 1N4007. It doesn't matter. It's a 1000 volt 1 amp diode. We're going to go through a resistor that's kind of like a snubber. Its whole job is to kind of reduce any kind of switching noise or anything like that and give a little bit of current limit. That is going to feed a 4.7 microfarad 630 volt cap. Now, that's that big rectangular one I talked about in the last video. I updated the Gerber files for the board, for the circuit board, to accommodate either this exact capacitor if you want to buy one, or do something like this with a pair of capacitors in series. And there's the mounting for either one there that you can mount either or. From there, and there's going to be a lot of ripple here because if you notice, this is only a single diode. So instead of seeing this, when you have this AC signal here, what's going to come out here is going to look something like this. And then that negative waveform will be, well, hold on. Let's fix that. You're going to see something like this. The negative waveform, and then nothing during the positive, then another negative waveform, nothing during the positive. So you're just going to have this giant ripple here. There's going to be an entire half cycle where there's no voltage. So that's going to put a huge amount of ripple here. And so this cap has to be able to handle that. That's why I put that film cap in there. It really won't hurt. You could put an electrolytic. It would be fine. But it's what I had. It's what I used. Coming out of there, 150K 3 watt. That's just a dropper resistor. Because we're going to, again, this is going to go to the negative peak. It's going to be 565 volts. Eventually, this will charge up to 565 volts. And I have to drop it down to 150 volts. Negative. So this resistor does that. And since this is going to be almost zero current, because bias supplies don't really draw current, you're just looking for a voltage reference. The grid of a tube is extraordinarily low current. Like, you wouldn't be able to measure it almost, but it's there. It's just tiny. And then we have this 470K, so you have a divider. See this 150 with the 470? That's your voltage divider. That's going to give you more than 150 volts negative. And then the little bit of extra is going to be cropped off by this 150 volt Zener diode. So it's 150 volt, it's only a little half watt. Or you can use two 75 volt half watt Zeners. I have on the board, I have an accommodation to either do the 2 series diodes or one bigger diode. And that's going to give us a nice solid negative 150 volt supply. 2 10K resistors to isolate the 2 channels so you don't really get that much crosstalk between them. And if something goes wrong, you know, you have this 10K resistor between here and here. So that's it. So that's your bias supply. Now next we're going to talk about this 300 volt supply, and that's going to be the rest of the video here. I'm going to zoom you in on one section, and hopefully we won't get too much shutter roll. All right, I think I might be seeing a little bit of shutter roll on there, but hey, it's the best I can do right now. All right, so just looking at one of the two, these are identical supplies. One is for channel 1, the other's for channel 2. And these are going to feed, looking here, these are going to feed our cascodes. So you can see 300 volts here, and they're also going to feed the cathode followers. 300 volts there and there. And because these are voltage amp stages and there's really not a lot of current draw, this whole mess here probably won't draw much more than, you know, I don't know, tens of milliamps. That's it. So here's the cool part. I'm going to talk about this in two clips. First thing we're going to talk about is this choke, because there's actually more to know about this choke than there is about this regulator circuit, believe it or not. There's two ways that a choke can be used in a power supply. One of the more common ones is where it's used as a filter, you know, like for noise. And that is very different than when it's being used as an actual, what we call a reactor. A reactor is when the choke actually goes between the unfiltered rectified DC and your output. Believe it or not, even without this capacitor, if I put the correct load on this, and that's a critical thing right there, the output of this choke will be DC. There won't be any ripple on it. It'll be clean. It'll look the same as if you had a capacitor on it. But some of the math is different because of the way the inductive reactance works. Now, when you buy a choke, here, let me get one. Like here's one right here. They'll have the specs written right on the choke itself. So you can see this one is 12 henries. It says 80 milliamp DC and 375 ohms. Now, what does that mean? Well, let's take a look. There, I just grabbed my other meter because it had probes in it already. All right. And if we go to ohms, about 370 ohms. So this said 375. So you can see that is the DC resistance of the actual windings. So inside here, there's a lot of little, you can see how many layers of paper there is. There's a whole lot of windings in there. And it adds up to about 370 or 375 ohms resistance, DC resistance. So that's the DC resistance of the coil. We'll find out why that's important in a moment. 12H stands for 12 henries. So when we're talking about an inductor, that is the actual inductance of the coil. And if we put a meter on it, let's see if I've got something that'll measure that high. Okay, we'll put our LCR meter on it. And you can see it says 12 Henry. This one's reading it at about 13 Henries. And again, that can change. You can see when we change the frequency, there's 10 kilohertz, 100 kilohertz, 100 hertz. So you can see how it will change a little bit depending, and that has to do with the meter itself. There's loading, there's all kinds of things. Chokes are funny things. They change their characteristics based on what you're feeding them with. Frequency, duty cycle, current, voltage, all these things are going to affect this. That's what we're going to talk about, and that's why I said this deserves its own little clip. But let's just say it's 12 henries, all right, because that's what they're calling it. Last but not least is this 80 MADC. What does that mean? So when we say 80 milliamp DC, that is the maximum current that can pass through this coil, through this inductor, and it still acts as a 12 Henry inductor. We call that being in reactor mode. All right. But there's another rule that they never put on these. I don't know why they don't do it. Well, I do know why they do it, because it varies. And that is what you call the critical current, or the I sub C. And the critical current is the minimum current that this coil needs, or this inductor needs, in order to act as a reactor. We'll get into that here in a minute, and the math that you have to use to calculate it, but it varies with the voltage that you're applying on the coil. So that's a big thing. You have to do all the math. That's why you can't just go online and buy a choke, a random choke. All of these things come into factor if you want to use what's called a choke input power supply. And that's exactly what this is here. This is a choke input power supply. If you look again, move this over here. If you see here, I have two more diodes. And yes, because the way they're facing this way, they are not interfering with these diodes. Don't try this with bridge rectifiers. And don't try this in anything where this output and this output are going to be tied to the same point. You will have big problems, because one diode will hog more current than the other, and it'll act like a short, and you can have all kinds of problems. So, but the way we're doing this, it works. So we have a unfiltered, rectified 400 volt AC signal here. And what you're going to see is a rippled, 100% ripple. And it is going to be 565 volts peak. And it's all going to be positive going. So it'll be DC with 100% ripple. Now, that ripple is really important. If you put a capacitor here, this choke can no longer work. The choke requires AC. It requires an AC signal. And the frequency of that AC signal will affect how it works. In addition to the frequency, the amount of voltage you're applying will affect it. In addition to that, the amount of current flowing through there will affect how this works. Everything has to be in its range. It has a range of voltage and current and so forth that it'll operate in. And if you go outside of that, then it will not be a reactor anymore. It can still be somewhat of an inductor, depending on how much ripple and how much AC component there is to this. But it will not work as a 12 Henry inductor. And eventually it'll act more like a 224 ohm resistor. In other words, the load here will see more of the voltage drop because of the winding resistance than it will from the actual inductance of the choke. Now, in order for this to work, you have to have a minimum current, not just the maximum current. You have to operate between that. And that minimum current we call I critical, and it is affected by the amount of voltage and the rated inductance of the coil. And if I move this over here, there's a little note there. I critical. Now, this is for 60 hertz full wave. Okay, so if you're looking at 60 hertz full wave rectified, this is going to be the formula. If you're looking at 50 hertz, or if you're looking at 60 hertz half wave, this constant number here changes. So if like 60 hertz half wave, this would be 2260, I believe. I think you double it. I could be wrong. You EE people out there can correct me. So the critical current is the voltage, and when I talk about voltage, that's the choke output voltage. So the voltage that will be coming out of here, and we can calculate that in a minute, divided by the constant 1130, and I'm not going to derive that because it's big long explanation, times the inductance in henries. So in our case, the output of this choke, when it is working in reactor mode, will be 0.9 times the volts RMS. And again, I'm not going to derive how that happens, but in an inductor, your output of the choke is going to be 0.9 times VRMS when the choke is operating in reactor mode. So if you take the 400 volts times 0.9, you'll get 360 volts. So if you put 400 volts RMS in here, you will get 360 volts DC out here. So that's DC. And believe it or not, if you put the right load on it, you won't even need this capacitor. The capacitor is good for surge currents and things like that, but it'll actually work without it. You could actually just have come straight out of the choke and it will look like a very clean DC. It'll have a little bit of ripple, kind of like a capacitor does, but it'll work just like a capacitor. Pretty cool, huh? Now, I'll talk about this whole thing in a minute, why I want 360 volts, but we'll get into that later. So again, if I take that 360 volts, which is the choke output after we calculated it, right, divided by 1130 times 12 henries, because the chokes that we're using are also 12 henry at 80 MA, but they have a different DC resistance. Theirs is 224 ohms on the toroidal, and it's a toroidal coil or choke. This one's just an EI square choke, and it's got 375 ohms. So the winding is a little bit different on this one than on the toroidal one. But other than that, they're both 80 milliamp and they're both 12 henry. So 1130 times 12, so that would be 360 divided by 13,560, and that's going to be 0.0266, which is going to be 26.6 milliamps. So your critical current equals 26.6 milliamps. And your maximum current is 80 milliamps. So to stay in reactor mode, the current of the inductor must stay between 27, that looks like a 1, doesn't it? 27 and 80 milliamps. If we go above 80 milliamps or below 27 milliamps, what's going to happen is this is going to stop being a choke input power supply, and it's just going to be a filter capacitor input power supply with a filter choke on it, not really a reactor. Now, what's the advantage of doing this? Because, you know, it sounds like a lot of parameters. You basically need a really specific choke for what you're doing, and that is why you don't see these very often. There's a couple of common values for tube amps that are still being manufactured, one of them being this Antec LK-12H ADC. And it just so happens it's going to work perfectly for what I want. Because here's the thing. If I used a capacitor input here, I would have 565 volts here. I want 300 volts out. I would have to drop 265 volts between here and here to get my 300 volts. All of that is going to be converted into heat if I just used a resistor or something. Or if even using a pass transistor and using a linear regulator, this is going to have to drop 265 volts from the collector to emitter. That's going to be an incredible amount of heat. So you're wasting tons of power on heat. Wouldn't it be nice if we could drop that voltage without turning it into heat? And that's exactly what this this reactor is going to do. It actually, instead of charging up to the peak, it's actually going to drop the voltage to 360 volts because of inductive reactance. In other words, the voltage is going to lead the current by 90 degrees. So what's going to always happen is because that's always going to be, current is going to be lagging behind the voltage, your actual voltage here is going to appear, because of the load you're putting on here, to be lower than the peak by 0.9 times the RMS voltage. So I'm going to have 360 volts here, and since all it's doing is delaying, it's storing energy magnetically. So it's converting that energy into magnetic energy and then converting it back into electrical energy. And in doing so, with that delay, you're not converting all that energy into heat. And so without creating heat, I now have 360 volts here. And now I only have a 60 volt drop from here to here, which is going to be way less heat and way more efficient than if I just put a gigantic resistor in there. So you see how nice that is? Now, the way this thing is designed, we'll get into that next, okay? Here's the problem. When you first turn the amp on, the tubes are not warmed up. The tubes are not going to draw any current. So this is going to go high impedance. There won't be any load on it, or be very little load, see 220K. And as a result, this will no longer be above its critical current level. It'll be below the critical current. And then this is going to be pretty much like, more like a partial reactor. So what you'd see here when you first turn the amp on, this is going to be up over 400 volts. It's going to be between 400 and 500 volts right here. You know, something like that, 400 to 500. And then as the tubes warm up, it'll start to draw current. The current will go up here. When it crosses that 27 milliamp threshold, this will drop all of a sudden down to 360 volts here. And then from that point on, you just have a very low voltage drop here and not a whole lot of current, because it's just tens of milliamps. So this thing's going to run super cool. You don't need great big heat sinks. You don't need fans or anything like that. And this will sit really nice at about 300 volts. Now, there's one caveat to that. You have to have a Zener reference for this power supply. So let's talk about that now. In order for this pass transistor to work, this base has to be held at a reference level. And in our case, I want it to be 300 volts. And so let's ignore this for a minute. If I put two Zener diodes in series, 150 volt ones, that will clamp this section right here off at 300 volts. So right here's 300 volts. The problem is any voltage above the 300 that I'm dropping off is going to be burned off in these as current. So you would have to put a dropping resistor in there to kind of limit that a little bit. And that's what this 10K does. The problem is that'll all work really well, but if I put that from here to here, when this thing is not in reactor mode, this voltage is going to be really high. It's going to be, 260 volts or 200 and some volts higher than when it's loaded, which means all that extra current is going to get dropped across all of this. This whole stack is going to run at much higher current. If you raise the voltage, it's going to increase the current. And as a result, this 10K is going to get hot, and these are going to get hot. When these big diodes, high voltage Zener diodes, run in the avalanche mode, and you can look that up. And what happens is, as they heat up, their Zener voltage will increase. And on this particular diode that I'm using, it'll increase approximately 0.1% for each degree Celsius you raise this above ambient temperature. So what happens is this 300 volts will creep up. So it's a moving target, okay? Well, I don't want that. And then on top of that, once this starts drawing current, I need base current because the gain on this big transistor is only about 15. So if a beta of 15, if I need, 30 to 50 milliamps here, I'm still going to need, a couple of milliamps here. So that's going to increase this even more. These are going to get hotter. The voltage is going to rise. It's not good. So what I'm doing is I'm coming off of the plus 525 up here, and I'm feeding it directly in there. This isn't going to move. It's going to stay pretty solid up there. And if it fluctuates a little bit, at that level, it's not going to matter. Once it settles in with this, it really doesn't care what's happening here because it's a separate current source. Feeding that in there, this will drift a little bit till it stabilizes, and it'll go up to a little bit above 300 volts. And you can see what I did was I put a third Zener diode between here and here, and all that's going to do is that's going to take some of the load off of this 10K. So I don't have to convert so much to heat here. So this right here is going to be clamped at 450 volts. So the drop between here and here is going to be between 450 and whatever this is sitting at, so let's say 545, 550. So you're going to have about a 100 volt drop across here divided by 10K. Okay, so you're going to have somewhere around 10, 11 milliamps. That's good. That's what we want. These will kind of settle. They'll go a little bit above 300 volts, and then it'll just sit there forever like that. And no matter whether this is in critical mode or not critical mode, this will stay at 300 volts. Now, once this thing starts drawing current, when the tubes warm up, this is going to need more current, but I put this little Darlington transistor in here. See what that does? And what that's going to do is that's going to make this transistor look like it has way, way, way higher gain than it actually does. So the current feeding this is only going to change microamps or microamps. And so this is going to be rock solid. Even when this thing is below its critical current, this drop here isn't going to matter because the only current you're drawing is through this 220K resistor just to kind of make it stabilize on something to 300 volts. And as a result, this won't get hot. Once this draws current, this is going to drop down from its 400 to 500 volts. It's going to drop down to 360. This voltage drop drops. This stays 300 volts. This still stays cool. Even though there's more current here, there's less voltage drop, so it stays cool. The name of the game is, no matter what happens, whether I put a load on here or no load on here, whatever, this all stays at one ambient, settled temperature, and it stays there, and it's rock solid. So once this stabilizes, it's not going to change, and it's bulletproof. So if something goes wrong, if one of the tubes, a filament opens on the tube, so the tube doesn't conduct, and this, the current drops way down, and this shoots way up, this is still going to be safe in here. And that's the whole point I'm using this reactor. Again, do I have to do this? No. This whole thing could be replaced with a couple of resistors and capacitors. Big resistors that are going to drop a whole lot of current. And the problem is, as things sag, it'll change with it. So, would that matter a whole lot? Probably not. And this would work with a resistive driver, dropper. But as I said earlier, I wanted to work with this reactor circuit, and I wanted to work with this regulator, high voltage, to see if I could make it work. And it does. It works exactly as I'm saying. You'll see that in a minute. Okay, so just to look at the full schematic again. There it is. Okay. Here's my notes. Just talking about what I was saying with the Zener stack here. The notes on the Zener diodes themselves. They're 1N5383Bs, 150 volt, 5 watt avalanche type. Temperature coefficient is somewhere between 0.08 and 0.12% per degree Celsius. So that on average, you'll see about a 0.1% change for each degree Celsius. So that means if this thing raises 10 degrees Celsius, it'll go up by 1%. So your 300 volts will then be 303 volts. And because this is the 5 watt Zener, they will heat up as they dissipate. I did not cut any lead length off of these when I mounted them. I left the entire lead length in there because the leads are actually part of the heatsink and they are baked into the formula for the maximum wattage of these. If you cut the leads off on these Zeners, like when you put them down on a board, you just reduce the amount of airflow around it between the board, and you've also reduced the amount of heat sinking from the leads on there. They have big, thick wire leads. You've derated your Zener diode. It's no longer 5 watts. Just remember that when you work with components like that. All right. I hope that explains it all. And I hope I didn't confuse you all or bore you all too much. But let's put this thing back up on a bench and test it. Okay, here we are. And the first thing I'm going to do is I don't have anything connected as far as a load. We're going to power this thing up totally unloaded. So we're going to give it the worst case scenario. What happens when you turn the amp on and none of the tubes are warmed up, nothing's connected. It is literally just running unloaded. Okay. I hope you can see this. It's hard for me to see on the camera whether things are... Yeah, I don't know. Let me shut this back light off. Maybe that will help. Ooh, that does help. Okay. All right. So let me turn on, I have that on. And again, there is no load. And we're going to connect this meter over here to our B plus line. So that's going to be where the, right here, the 520 B plus. You'll have to take my word for it, but right here is one of the spots that goes directly to the B plus. Then we're going to take this meter down here and we're going to connect it to the output of the 300 volt regulated supply here on this side. Okay, they're both going to read the same. And I'm going to be really careful because since there is no load on here, even though there are bleeder resistors in here, it will hold a big charge for quite some time. And as a result, I'm going to get my discharge box right here. And I'm going to just keep it handy here. All right. So let's power it up and let's see what it does. Remember, everything's unloaded right now. So that 400 volts should pretty much be somewhere around 560 volts somewhere. They're going to get a little bit of drop through here, but I bet you this is going to be a lot higher than that. But our regulated should stay somewhere around 300 volts, and it will creep up a little bit as the diodes heat up. So you should see that happening as well on this meter. So this should be 300 volts. This should be about 460. All right, ready? By the way, there is no dim bulb on here. It's full power. Contact. Look at that, 566. That's pretty close. And look at that, 300, and it's creeping up as the diodes are warming up. Now let me show you something cool. See that 306 volts? Watch what happens if I blow on it, on these diodes. See how it dropped a little bit? And these will keep creeping up for a while, and it'll probably get somewhere around 310 or something like that. Maybe a little more. Won't hurt anything though. This circuit is designed to work at that voltage. And you can see this is just staying pretty solid. Now if I turn it off, it's going to take some time to discharge. So what I'm going to do is I'm going to put this up here right now, like this, so you can see it. And I'm going to go from ground to the output. And there it is. We're all discharged. Now, if you wait long enough, these little bleeders here will bring it down, but not that fast. All right. And you see it'll give you a little bit of, it'll charge back up a little bit. That's what electrolytics tend to do. Now let's put a load on these. So on the 300 volt supply, I have a couple of 10K 25 watt resistors. All right. So 10K, let's do the math. I'll do it right here on a calculator with you. If I take 300 volts, let's just say 310 even, divided by 10,000, that equals 31 milliamps. So I'm going to put about a 31 milliamp current load on this. And if you times that by the 310, it's going to be about 9.61 watts. All right. So let me get my couple of jumper leads. Give me a second. Okay, I have both of these resistors connected to ground now, so they're actually acting as 10K load resistors. So I have 10 watt, about 9 point something watts here and 9 here. So you have somewhere around 18, 19 watts total on these 300 volt supplies combined. And you'll see this is really not going to do a whole lot. It's going to do about the same thing, and this is not going to do a whole lot. So here we go. And you can see it's starting a little bit lower now, but you see with the load, once it drifts up, it's going to be a little bit over about 305 volts or so when it settles. But it's going to be real close to that 300 we want. And you can see this drops that a little bit. Instead of 565, it's 561. All right. So let's turn it back off. And now let's put a load also on the 300 volt B plus supply, or the 465 volt B plus supply. So I actually have a DC load, but it has a maximum voltage limit of 500 volts. And so I can't use my fancy DC load, so I made one. So you can see I have my little fan, little USB powered fan over there. And I have a whole bunch of 30K resistors in series parallel. And I have about, this is a little over 5,000 ohms or 5K. And if you take 400 and let's say 450, or I'm sorry, 550 volts, I'm just saying roughly when it with some drop, divided by 5,000, that's 110 milliamps. And you times that by the 550, that's 60 watts. And that's going to be similar to where these amps are going to be idling, 30 watts each side. So this is going to be real world scenario. And with this, you need this fan because even with this big block of 25 watt, there are 6 25 watt ceramic resistors in there. They will still get hot. All right, power on, and we'll see if this is still 560 volts. And see now, we're down around 540. And again, I expected it to be 520 to 530, but realistically it's 540. And you can see this is going right up to our nice 300 volts, and everything is happy. How you like that? Perfect. All right, I'm going to turn this off now. And you can see how fast it bleeds down now because you have that huge load on there. See, it's all down already. And then now what I'm going to do is I'm going to get away from our 100 volt, our 300 volt supply. I'm going to put this meter like this. Give me a second. Okay, I'm still connected to ground, but now I have a probe. This hand is nowhere near that chassis. I'm going to put it behind my back. This is called the one-hand rule. Your heart is on the left-hand side of your chest. So you use your right hand, and I'm on big, thick rubber-soled shoes on a rubber mat. And so even if I did get myself across that voltage, what would happen is it would hurt my hand really bad, but I would not get electrocuted across my heart. So hopefully I would live. But I'm not going to do that. I'm going to be very careful. So the first thing I want to check is I want to look at my negative 150 volt bias supply. And that's going to be right here, this purple wire. This should go to somewhere around negative 150, and it might be a little bit low, it might be a little bit high. So let's check it out and see what it does. And I'm not going to stay on there for a long time because I don't want those resistors getting too super hot. But I'm going to hold this on here, turn it on, and you can see negative 151 volts. All right, negative 151. And yes, I did cross over my hand there. I'm being careful though. Negative 152. So that's right what we expected. All right, power down. Give my resistors a minute to get the air on them. And now we're going to look over here at our elevated filament supply. So we should have somewhere around 90 some volts here and 100 and some volts here. So this is for the 6SN7, and this is for the 6N1 for the upper part of the cascode. So in other words, these two filaments are going to be elevated to about 96 volts or something, and these two filaments are going to be elevated to about 110 volts, something like that. And we can check that all right over here. So here's the 96. Let me turn on. Here's the 96 volts. And it's sitting at about 99. So it's about 3 volts high. And then here's the 108 volt. And it's 111. So that's good. Elevated filaments. And that's going to be just right for that. So those are good. Turn back off. Last but not least, it's not on the schematic. It's on the board, but not the schematic. If you remember, we have this constant current source for the tail of this differential pair. So this is a cascoded differential pair, and this is really what makes this a Hedge amplifier, okay? And what we're going to do here is, instead of a resistive tail, like a resistor that they put on there, and I think that's what Hedge actually did, we're using a constant current source, which means if this voltage is not exactly 300 volts, it's still going to divide the same percentage with this resistive divider, but the current's always going to stay stable, so it's not going to hurt anything. Give you more headroom, if anything else, a little bit. So we need that negative 12.6 volt source to power this, right? Remember those little boards that I made and showed you in the last video for the constant current source? We need to feed that, and that's what this is up here in this corner up here. And that's actually your negative 12.6 volts. And I actually set this regulator to be at negative 15 volts to give it just a little more headroom. So let's turn on. And again, we're looking at this meter. And let's go to right there. And look at that. Dead on, negative 15.17. Okay. All right, that concludes this video. As I said, you could just have easily used a bunch of resistive divider networks with capacitors and so forth and derived these voltages that you needed for the most part. But you're making a lot of heat, and you're dealing with big power resistors, that sometimes those resistances are hard to get, to purchase, because unless you get into like precision ones and so forth, it's hard to just use standard value power resistors. So, and it's less efficient. You're converting a lot of your dropped voltage into heat, which we don't want to do. So you can see this is going to be perfect for our Hedge amplifier, and we're ready to progress forward and actually build the amplifier. And that's what the next video is going to be. We're going to actually build the amplifier and get it to a power up point that we can check the bias, and that'll be the next part. So I hope you enjoyed this. I know some of you probably did. Some of you probably pulled your hair out. But either way, I hope you enjoyed it somewhat. I wish you all the best, and as always, I wish you all peace, joy, happiness, and good health in your lives, and hope all is well with all of you. Take care, and as soon as I can get the next video out, I will. Just don't know when. Time, there isn't enough of it anymore. Anyway, take care, everybody. Bye-bye.